Actually, better send them to me.
But it's possible to have wireless connection here because.
Well, the only connection here is Eduroam, I think.
If you don't have Eduroam, you cannot.
The secretaries had a paper, the special sheet.
Maybe if you look on the
Where
registration.
did they give us a special sheet?
You should ask.
Yeah.
Yeah, we have foreigners here too. We're not in this department.
Yeah.
Yes. This is
Okay, hi everyone. So I'm going to be giving a course with on categorical quantum mechanics. So the difference to the course that Bob and Alex are giving is that their course doesn't explicitly make use of category theory. Of course, category theory is underlying what they're doing. And in this course, we're going to make clear, we're going to define and introduce the categorical structures that are at play, and we're going to emphasize that. So there's actually going to probably be quite a lot of overlap between our courses, but that's about the material we presented in very good ways. Okay, so this logo is QMAC, that stands for Quantum Mathematics and Computation. We've got that logo because we're based in computer science, but we're in collaboration with people here in the maths department. QMAC, fancy name for our collaboration. So if you give yourself fancy names, then you give you more money, that's the idea. So, categorical quantum mechanics uses monoidal theory and logic processes. Basic idea. So what do we mean by these things? Well, monoidal categories we've used before. We'll have a look at what those are again in this talk. What do we mean by logic? Well, this is something else that we'll talk about a little bit. The idea is that you don't only want to say what's happening in a procedure, you also want to have good techniques to prove why that procedure is going to work. It's a fundamental idea. And that's the general notion of the word logic that I'm using. Logic is something that lets you not only represent the physical or informatic processes that are taking place, but also reason about them in the general sense that you can deduce that if I do these things in this order, I'll have this overall effect. Okay. So these 4 lectures that Chris and I will give, very broadly we'll cover these topics. So controversially I'm going to start with 2 categories. So lots of you might have seen monoidal categories before. So to spice things up a bit, I'm going to not introduce monoidal categories, but introduce 2 categories. Now it's not as terrible as it sounds, because actually 2 categories are basically the same as monoidal categories. It's a crying shame that people want to talk about them more. So just to make things a bit interesting, we're going to present them by that route in this lecture. And then from 2 categories, we've already then got monoidal categories essentially, and we're going to talk a little bit about some of those basic categorical constructions that underlie the sort of things that Bob was talking about. Alex is going to give, Chris is going to give some lectures on Frobenius algebras, operator algebras, and quantum mechanical channels. And in the last lecture, I'll use some of this 2 categorical generality and show what 2 categories can do with quantum computing. That's the idea. But if you wanted, you could wait a few months and just buy the book. There's a book coming out with Cambridge University.
Oxford.
Sorry. I'm going to phone my publisher. All right. So I'm going to be compressing a lot of material into 1-hour lecture. So everything I say is going to be correct. I'm not going to give absolutely all details. In any event, the definitions of a lot of the things that I'm giving, you can just find on Google, on Wikipedia, on the NLab, on all sorts of online sources. So I won't worry too much about dry definitions, although I will give definitions. Worry more about the motivation for what you're doing, why things are this way, how it fits into the bigger picture. Please stop me and ask me questions if you want to. So let's start thinking about sets. So why do we care about sets? Well, set theory is supposed to be the foundation for mathematics. Except one who does mathematics seems to really care about that very much. You can't do much with a set. So you could, if you've got a set, you could exhibit an element of the set. Right? S, my set. Right, not much more really you can do, I suppose it's like set theory outside the foundation of mathematics. So how can we make this more interesting? Well, we could put a monoid structure on our set. If we have a monoid structure, we can multiply the elements. Okay, so here we've got some element S, an element T, we can multiply them together. The element is T. I'm not going to bother drawing any more sort of traditional approach to algebra, you might, took some different perspective, you might say my multiplication operation is m, it's a binary operation, so you might write m bracket s comma t close bracket. That would be sort of external notation. This is the sort of infix notation, which is about sort of high school level mathematical complexity. So of course we're all familiar with the idea that if we're adding up numbers, you don't write plus bracket 2 comma 3 close bracket. It's fine. 2 plus 3 equals 5. Why do we do that? Because it's a really good notation. Addition forms a monoid. Anyway, so why is it such good notation? This is something that you all worked out when you were about 15. Starting at the bottom level. Well, what if we want to multiply 3 elements? Now we've got a problem, because everything is fundamentally binary, and there are 2 ways we can do it. The left 2 or the right 2 first. Now the beauty of a monoid, right, the reason that a monoid is defined the way it is so that it doesn't matter which way you do it. The associativity property, of course, of monoid multiplication. All that matters is how our monoid elements are arranged along a line. That's all the associativity axiom says. Now this is the first sign, and it's a very profound sign of a connection between algebra and geometry. Why are the axioms for a monoid, for an algebra, the way they are? Why would the associativity unit laws, if you ever stop and ask yourself this, well, they're very mathematically nice, we can prove all sorts of, mathematicians rather, prove all sorts of beautiful things, developed into group theory, lots of fantastic theorems, it's the foundation to huge amounts of mathematics. But why those axioms? Why associativity and unitality? Why not some other axioms? Of course, there are many other structures with many other different axioms, some which are general and so on. But they don't seem to have had the broad impact in mathematics, which associativity and unitality. And I would say the reason for that is that the associativity law is profoundly connected to the geometry of the line. It just says, organise your elements along, and then they all have a new value, which will be the cost of those elements. Now really, the story that's underlying all of this work is that this connection between algebra and geometry goes far deeper than this. Of course, this is something that mathematicians have known for a long time, right? This is an observation. But if you really love this idea, and you really want to make precise what is this connection between algebra and geometry, it's a category theory that's almost exactly designed to let you do it. In fact, just as the notion of a monoid, now say, is exactly designed to allow you to arrange elements on line and make sense of them. So category theory is just exactly perfectly designed to allow you to arrange mathematical structures in higher dimension. Just exactly what category theory is from a modern perspective. Not, of course, how it was motivated or how it was discovered 50 years ago. It was. Now, there are some sort of trivial things we could worry about here. Do our elements label points on the line, or do they label line segments? Right? But it's a totally boring question, right? It's not some deep philosophical conundrum, make any bloody difference. Right? But it's interesting that we do have these 2 perspectives nonetheless. Right? There isn't a single way to view our lines as rising, kind of being connected directly to these elements. There are 2 different ways. This level, they're obviously completely equivalent and there's no way to choose one over the other. But in general, we will find that these dual perspectives do behave completely differently. And that working with this duality, essentially the duality that says are our elements points or segments, will completely change the flavour of the mathematics. And being aware of these essentially notational issues have been an extremely important part of the subject, and understanding exactly the relationship between these perspectives has been a cultural shift in mathematics. I don't think that's too dramatic to say, which has enabled this work to take place. In some sense, that's again restating what Bob said. See why that is. Okay. So now, sorry, got a shot of light there. Right. So we've got these dots here. So let's go with this perspective for a while where our monoid elements label line segments. Now we've got these dots here, so Well, let's give some structure to those dots. Let's just assign labels. This leads exactly to the concept of a category. A category is just a monoid where it's a monoid with many points in this sense. So formally a category is a family of objects, ABC, dot dot, and for each pair of objects a family of morphisms in between them, in a directed sense, with an associative binary composition and unit morphisms for each object. So they just exactly say if you've got some morphism S from A to B, T from B to C, U from C to D, then all those times match up, so we can form this composition. This composition is unambiguous. It doesn't matter how we bracket it, that composition is T. There's also this requirement for unit morphisms. So a unit morphism on an object A would be a morphism from A to A, which when you compose from any morphism going out of A going into A, leaves that morphism unchanged. So what is a two category? Well, a two category is an extra layer of structure. The category. So it appears in this picture. That's not really a very good way to define it. It's not how you define it. But the two category allows you to draw basically the same sorts of pictures, except now morphisms with common source and common target can be related to each other in an interesting way. Those relationships are called two morphisms. So here, for example, S and T compose to give a morphism from A to C, and there's another morphism from A to C called V, and there's a two morphism that goes from the composite of S and T to V. We call that alpha, and in this notation alpha is drawn with this double arrow to show it's a two morphism, and we think of it as filling in that entire half circle. Similarly, beta is a two morphism from W to the composite of T, U. So that's the sort of picture we'll draw. Yeah.
So are you allowing monomorphisms of Helm sets and not match between arbitrary Helm sets?
This is not a definition of a two category. This is an example of the sort of picture that we can draw. So we'll come to the definition of a two category later.
Okay.
So don't worry too much about this. Precise thing. Okay. Now this is all well and good, and this sort of picture is called a pasting diagram. You see this a lot in the literature. And the idea is that not only can we compose morphisms, S, T, U, and so on, but we can also, when they're part of a single, well-formed diagram like this, compose two morphisms. So this two morphism beta and this two morphism alpha, they're interacting, as it were, across this morphism T. All these boundaries are correct and so on. There's no type errors being made. So in a two category, we can compose this pair of two morphisms, a single composite two morphism. The source of the two morphism will be S composed with W, and the target of the two morphism will be V composed with U. How do we form that composite? Well, we will normally just draw this picture. Now the problem with this is that if we start drawing very big pictures, very big planar diagrams of this sort, it can become extremely difficult to really see what's going on. Because this is quite a busy, fiddly notation actually. And especially if we have certain equations that relate certain composed two morphisms with certain other composed two morphisms, and not make use of those equations, it can be extremely difficult to see where those equations can be applied. So this is a big drawback with the pasting diagram notation for two category theory, and it's what gives two categories a bad name in my book among non-pure mathematicians who use this sort of mathematics. So what we're going to do is we're going to look at that dual perspective that we saw earlier, the dual perspective that said these elements S, T, U, do they have to be points or line segments? So what's the dual of this picture? It's just this. It's completely different. A lot more colourful, right? That's the diagrams. Oh, this is how I put the colours in. But the point is, it's exactly the same. In fact, I've cunningly arranged it so that every single element of this diagram, apart from the labels on the arrows, which I've dropped, I maintain from one slide to the next. So the A, B, C, D stay in the same place, the alpha, beta stay in the same place. And the STU should have stayed, sorry, that's a mistake, those STUs should be there. The S should be labelling this line here, the T should be labelling this line here, the U should be labelling this line here. Should have all been there. So what is this dual notation now for a 2 category? We're richer now because we don't just have a line. Well, the idea is that the objects A, B, C, D, which were originally points, they're now regions. The morphisms S, T, U, V, W, which were originally lines with a horizontal aspect, and are lines with a vertical aspect, passing through those original lines exactly once, if you imagine the two diagrams being superimposed on each other. And these two morphisms, alpha and beta, which were assigned to these fill-in regions here, now are localized to points. So the dimensionality of all structures has been inverted. Now this dual notation is far superior to the original Hastings diagram notation. One reason is that we can drop a lot of the detail without loss of generality almost always. Because as long as we know the names of the two morphisms, alpha and beta here, we can reconstruct everything else. And calculationally, of course, you could do that here as well, but it would be a lot less useful from that perspective. This dual notation we call the graphical calculus. That's what the graphical calculus is. It's easy to get the impression that the graphical calculus is some completely bizarre, totally new way to draw and represent with the structures that make up a monoidal method. But it's not, it's just completely equivalent to the original boring Hastings diagram notation, dual. Like I say, often we'll just draw our diagrams like this, we'll drop a lot of the fiddly details around the edges, and they can be easily reconstructed. So why is this fundamentally more useful? What's the fundamental reason? Well, when you use it, it just becomes totally clear why this is so useful, but it's somehow difficult to express, difficult to put into words. The best attempt that I can give is to say that fundamentally we want to use these two categories to describe processes in science, physics, mathematics. And there's all sorts of, this is very broad, different areas of science, they're all modelling very different things, but there's a lot of commonality. In particular, in all these subjects, we don't study the processes in the most arbitrary sort of sense. We always study local processes, processes that only do things depending on the resources they have locally available, and then that produce their results locally. That's a fundamental feature of science, quantum computing, information physics, large areas of mathematics like topology, and so on. Locality is extremely important. Now, what are, in the real actual uses of this mathematics, what are the processes? Well, it's not the object A, B, C, D. It's the two morphisms, alpha, beta. They're the processes, they're the dynamics, they're the things that are actually happening. And they're happening at some point, making use of some resources, and then emitting some resources. So that's fundamentally, for me, why this notation is superior. Because the things that are happening locally are drawn locally as points rather than regions. That's why it's so much more natural. Okay, so what is a two-category formally? Again, this is again quite compressed. I'm sure it's correct, but you shouldn't take this as the best definition of the two-category. You should go and look up in a textbook, and you'll get something that's a bit clearer, but a lot longer, a lot more expanded. Okay. And by the way, when I say two-category, I mean fully weak sort of algebraic structure, the sort of thing that would often be called in other places a weak two-category, or maybe a bi-category. See what we mean by that weakness at the moment. So this is a bit of a cultural shift that's happened in the last 5 or 10 years. People have started recognising that these weak structures are the most important things, and calling these things weak two categories all the time, just calling them two categories. So I try and jump on that bandwagon, all the cool kids are doing it. So, what is a two category? Well, it's got a family of objects, and for any pair of objects, it's got a category. From A to B. Objects, this category of morphisms, and the morphisms of that category, usingly, are the two morphisms of the category. Question?
No, I was just
Okay. Right. And as we've seen, we'll typically draw these things like this. So these lines are objects of this category, and this double line alpha morphs with this category. Typically, we're going to call these A, B objects, these lines morphisms, and these double lines two morphisms. We require well-defined horizontal composition. So the idea is that if we've got alpha, beta, gamma, delta, which we can arrange in this way such that all the types match up, then this composite structure is a single two-morphism which is in fact well-defined in the following sense. It doesn't matter if we compose alpha with beta first, and separately gamma with delta, and then stuck the results into each other horizontally, or if alternatively we compose alpha and gamma horizontally, and beta and delta horizontally, and stuck the results together vertically. No matter what we do, the result has to be well-defined. So the final big piece of structure that a two category has, which makes it weak, are the associator unit structures. Let's see what these are. If we've got three morphisms, ST and U, which we can compose in the manner we were seeing earlier on the chain, then there are two ways we can compose them. U with T and then S, or we compose U with T and then S. And in two categories, these will not be the same morphism. And we don't require them to be the same morphism. We do require that there be an invertible two morphism alpha for each U, T, and S that goes in between. So these morphisms, they're objects in this Hom category A, D. The idea is they're not equal objects, they're isomorphic objects. And not only that, we've chosen a particular isomorphism, which we call alpha. We also need unit two morphisms. On the left and right, I'm only going to draw the left ones, right, similar. So for any morphism S, we could compose S with the unit morphism for A. And that's an object of this Hom category A, B. But S is also an element of that Hom category A, B. Those have to be isomorphic objects. We have a canonical isomorphism, which we call Lambda. So we'll get one of these for every morphism S.
So
And
the strong
similarly on
notion,
the other side.
strong notion would actually be imposing equations.
Right, so the strong notion, which is called a strict two category, is where this morphism is identical to this morphism. This composed morphism is identical to this. It's the strong notion. Okay, so what do I mean by coherent here? Well, that's extremely important. Coherence means essentially that any well-typed equation that only involves these alpha, lambda, and the part of lambda rho structure that I've written. Any equation formed just from these alpha, lambda, and rhos that's not a malformed equation must be satisfied. Coherence. People will talk about more about that later. So let's use the graphical calculus, the dual notation, to look at all this structure. So our two morphisms are fundamental structures here. We have little vertices, as we've seen. Their sources and targets, the source at the top, target at the bottom, were horizontal lines, now they're these vertical lines. And the source and target objects for those morphisms, A and B, are now these regions, which we colour. It's a nice way to do it. The fact that horizontal composition is well defined just means that this picture is unambiguous. Whenever we give pictures like this of composites for two morphisms, we don't need to bother saying whether we compose them horizontally first or vertically first. So that's the sort of thing that Bob is talking about. Now, how do we draw pictures of these coherent structures? Well, suppose we've got
Jamie, sorry to interrupt. Just to be sure, your alpha and lambda need not even be isomorphisms.
Now, I want them to be isomorphisms, and I should have that. It's a mistake.
Yeah.
So for said that, but I didn't write that down. Yes.
I was confused.
Right, so these morphisms, alpha, lambda, and rho, they have to be invertible. So what do these coherent structures, alpha and lambda, look like in the dual notation? Well, they don't look like much at all. And that's a surprising feature of the graphical calculus. Because if, from this perspective, they're extremely non-trivial. Right? There's a lot going on. There's this bracketing here, there's this bracketing here. We're filling this in here. There's sort of structure here. Right? It's very surprising that in the dual notation, these issues would simply become invisible. So this line is S, this line is T, this line is U. We compose S with T with U. It doesn't matter which way we do it. It doesn't matter which way we do it at the top. It doesn't matter which way we do it at the bottom. And we don't have to write anything to represent the presence of our alpha two morphism. It's completely invisible. Now, something similar is true for this lambda two morphism. It's a little bit more visible, so not necessarily. So let's just flip a few times to see what the dual picture looks like. We've got our morphism S here at the bottom, so that's this in the dual notation. And then our two morphism lambda. And then the source of lambda is the composite of S again here, that's this, with the identity morphism on A. Now here I'm drawing this identity morphism as dotted line. Okay? Something that we do sometimes. But a better notation, which is used more generally, is to not draw it at all, or nothing at all. And then this would just be a slightly deformed picture of lambda itself. Right, sorry. And then this diagram would be completely trivial. We'd have a little kink in the line. This wouldn't be here. Right. And this lambda would just be serving to mark a little kink in the line. Well, there's no need to mark it. It's not containing any useful information. So using a simpler notation, we could just have A, B, and a solid vertical line. So the graphical calculus trivializes all of the structure. That's why it's so useful. Yeah.
So on the left side bottom, where did the alpha go?
So I've drawn the lambda here. I really didn't need to. The alpha I haven't even bothered drawing here because there's nothing for it to do. That's the idea. Now I could have drawn it. But the fact that this graphical calculus works so nicely with these coherent structures isn't obvious. I could have drawn it. It's a theorem that you don't need to bother drawing it. I'm telling you, this is how I'm going to draw alpha. I'm going to draw it in this invisible way. So I should have done nothing more. Symmetrical has said this time I'm going to draw lambda, just nothing at all.
Could I just add?
Yeah.
What helped my understanding of the fact that you don't need to draw the alpha is that there's a top and a bottom to these diagrams. So there's something happening when you go from the top to the bottom, and that's the alpha. But you don't actually need to call it alpha.
James, exactly. Right. So at the top, we're composing the first two together, then with the third. So the idea is we're composing across B before we compose across C. In the bottom, we're composing across C before we compose after B. But that order of composition is simply not indicated in this graphical calculus. So correspondingly, there's no reason to also indicate this process alpha, which mediates between those two.
But if you were to draw it, what would it look like?
It would look like a circular blob called alpha, with 3 lines coming in at the bottom and 3 lines coming out at the top. And that would be perfectly good. That would just follow our general notation. In fact, it's the same symbol here. I should use the same symbol really. Except there would be 3 lines coming in at the top and 3 lines coming in at the bottom. Then I'd say, but we're going to use a new notation where we just don't even draw it at all. It's not obvious that that's superior. It's superior. Okay, so what is this coherence issue? Coherence, so the beauty of the graphical calculus is it completely takes away the need to worry about all these coherent structures. But you don't get it for free, right? It doesn't mean that certainly doesn't mean that we can just develop some new formulation of category theory which we don't have any of these at all. So we do need to worry about them a little bit and see what they are clearly. So one of the main basic results is that this is a very strong requirement. So any well-typed equation is satisfied, right? So it's very difficult to get a handle on concretely. If you've got some proposal for a 2 category, how on earth do you check that any well-typed equation is satisfied? There's an amount of work to do. Turns out that you only need to check these 2 equations. So they're called the triangle equation and the pentagon equation, because that's what they look like. And, well, let's look at the pentagon equation first. That says that if you've got 4 morphisms, S, T, U, V, then you could compose them like this, all bracketed to the left. You could compose them like this, all bracketed to the right. And there are 2 basic ways to navigate from that first bracketing to that second bracketing using these alpha structures. 3 if you go this way along the top, 2 if you go this way along the bottom. This is certainly a well-typed equation involving this coherence structure alpha. So by the coherence property, this equation will certainly be satisfied. First thing to say. What about this triangle equation? Well, if I've got 2 morphisms S and T that can be composed, then I could, if I liked first, compose S with the identity, then compose with T. I could then change my mind about that bracketing. Then I could use this lambda structure to eliminate that identity. Or I could have used the row structure to eliminate this identity in the first place. This is another well-typed equation that's just formed from these coherent structures, so we certainly need it to be satisfied in the 2 categories. So the theorem here is that these 2 diagrams for all STUV are all that we need to check. As long as all these diagrams hold, then in fact the data was completely coherent. And any possible well-typed diagram that you built just using the alphas, lambdas and rows, any well-typed equation rather, would in fact be satisfied. So that's the theorem. So, I'm not sure why. So this is a very important theorem. This is the second important. I'm not quite sure why it's the first. Probably because I wrote this slide first. I did. So what's this theorem say? For any object A and 2 morphisms alpha and beta that go from the identity on A itself. So alpha and beta are 2 morphisms. Their source morphism is the identity morphism on A, and their target morphism is also the identity morphism on A. Then we have alpha beta equals beta alpha. You can compose them in either way and get the same result. And proof is very easy to understand graphically. So here's alpha after beta. Let me just switch them around each other. Okay. So there's sort of no content there unless you buy into or you're happy with the proof that the graphical calculus is sound and complete. Now, maybe some experts in the audience can correct me. For 2 categories, I do not believe that there is a proof that the graphical calculus is sound and complete. For the monoidal categories, there certainly is. What do you think, Peter? Do you have some opinion? I mean, I had quite a careful look, and it really surprised me. Peter's written a very important paper on formalising these sorts of things in the case of monoidal categories, which are slightly more specialised in algebraic structures. Certainly nobody doubts that this graphical calculus is sound and complete. That is, anything that you can prove using the graphical calculus and basic topological manipulations, you can prove anything using the graphical calculus and basic topological manipulations if and only if it follows in the first place from the basic axioms of the 2 categories. That would be the thing you're trying to prove. Somehow it's too obvious, people don't even try and prove it. Somehow it's actually quite difficult to prove if you really try and say, what does that really mean?
Jamie, the argument is somehow some Ekman-Hilton style argument?
For this particular thing, yes. So now I was talking very generally about the question of whether something is true from the axioms of a 2 category, if and only if it flows from graphical calculus. This is a particular thing we could try and prove. And if you try and formalise this using the 2 category axioms and give an algebraic proof of it, it comes down to this thing called the Ekman-Hilton argument, which is familiar in algebraic topology. So And now I'm going to talk about duality. Dualities are the first really interesting sort of algebraic structure that we can define inside two categories from a particular perspective. So this is what a duality is. A morphism S from an object A to an object B has a right dual S star goes from B to A when there exist two morphisms eta and epsilon that satisfy these equations. Okay, so let's see, what are the types of these things? Eta must be a two morphism going from the identity on B to the composite of S star with S. Epsilon must be a two morphism going from the composite of S with S star to the identity on A. Eta and epsilon have those types, then this forms a big composite two cell, and we can require this to be the identity on S. So I'm being a little bit cheeky here, because the source of this composite two morphism is S composed with the identity, and the source of this two morphism is just S. Now those aren't the same, so the composite two morphism here and this identity two morphism don't live in the same set. So I can't really strictly ask them to be the same, but it's clear how I relate one to the other. I apply the row coherent two cell to eliminate this identity, and I apply the lambda coherent two cell here to eliminate this identity. Then I can formally compare this and this. The power of the coherence theorem says we don't have to worry about type mismatches of that sort, because we can always resolve them in an unambiguous way. The problem with the pasting diagram notation is that these type errors jump out at you. If you want everything to be perfectly well typed, I have to make these diagrams even more complicated, put these lambdas and rows on the top, which should be a lot of in-your-face, messy structure that we don't need to have to bother with. It's another reason why, well, it's part of the same reason we were talking about before, why the pasting diagram notation isn't particularly efficient. Okay, so there are these two sort of symmetrical conditions. This is duality. And in many category theory textbooks, you'd see this definition, and that would be that. Most of the time, they wouldn't even give it using this pasting diagram notation. They'd write it all out algebraically. They'd force these symbols, epsilon, eta, star, s, which clearly want to live in two dimensions, right? They would force them onto a line. Because here we're composing things horizontally and vertically, and traditionally the horizontal composition would be one binary operation, the vertical composition would be another binary operation, and you would just write this whole thing out as a linear string. That's how things are often done in traditional category theory. This is one step better, drawing it as these pasting diagrams two-dimensional. But what's even better is to use the dual notation. And then, and this is never done in these boring old category theory textbooks, where everything is made as hard as possible to understand. Right? And I bet there are category theorists out there who don't know what this looks like. This is one of the most fundamental sets of equations in category theory. If you use the dual notation, so you can see again, everything is staying fixed from one picture to the next. The A, B, eta, epsilon, S, S star, that is staying completely fixed. This is completely trivial notational change. Somehow the character of the equations completely change, and what's really going on jumps out at you in a very pleasing way. So from this perspective, we would describe these equations in the following way. Well, we've got two regions, A and B, with a border S that has A on the left and B on the right, and sort of dual border S star that has B on the left. And there's this vertex eta, which represents, sort of reading from bottom to top, the birth of a new A region. And this vertex epsilon, that represents somehow the death of the B region, absorbing into an A region. And if we connect them up like this, well then overall we've just got a single linear boundary that's with a bend in it. This equation just says to straighten that bend down. So, I can't emphasize this enough. Just made a trivial notational change, but the character is completely changed. Our interpretation of this equation is completely changed. It looks now like this has got something to do with topology, which you would never have guessed necessarily from this perspective. So what is this concept in traditional category theory? Well, if we work into two categories, in which the objects are categories, morphisms are functors, and the two morphisms are natural transformations, this is exactly the notion of an adjunction, which is really the first really interesting construction in category theory, the notion of adjunctions between categories. Pairs of functors that are equipped with these data, eta and epsilon, that's an interesting equation. This is an absurdly useful concept in category theory that crystallizes so many wonderful, subtle mathematical phenomena. And what's really going on are these topological pictures, right? So if I want to use the even more superior notation, which is only deficient in that it makes the correspondence, the dual nature of these diagrams slightly less completely obvious, I would have bothered putting these dot 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 lines in. This dot 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 is a stand-in for the identity morphism on the object B, which we of course had here. Here it formed an enormous part of the structure, right? It's this huge ugly line. Here I'm just drawing it by this little dot dot dot, and really it would be better not to draw it at all. So we see here that the notion of adjunction, generalized in this way to the notion of duality in our arbitrary two categories, is a fundamentally geometrical concept. Okay, so what is a monoidal category after all that? Well, a monoidal category is a two category with one object. That's what it is. Now, something simplifying in this case. We don't need to talk about objects anymore, we've just got one object. We're not going to talk about objects. We're not going to talk about objects and morphisms, two morphisms. We're just going to talk about objects and morphisms. And we're going to relabel things. So the morphisms of the two category, referred to as objects, the monoidal category, and the two morphisms of the two category, we're going to refer to as the morphisms of the monoidal category. Okay, makes sense? Simplify our vocabulary. Makes it a bit confusing, of course, if you keep transferring between thinking of a monoidal category as a two category, it's a category. In the graphical calculus, we don't label regions anymore, because of course those regions were labelled by objects of the two category. There's only one object, there's no need to label any regions. So instead of these nice multicoloured backgrounds, we just have white backgrounds. And in this case, the graphical calculus is very well studied. It's well known to be sound complete. Peter Solinger's got a very nice survey of how these graphical languages work for all different sorts of monoidal categories, collecting together lots of nice soundness and completeness proofs. But the crucial thing is that axiomatically, monoidal categories have just the same level of complexity as two categories. So, many people say, oh, I love monoidal categories, but two categories are too complicated for me. That's an absurd position to take. They're really not complicated. Now, what might well be the case is that you might know lots of fun and interesting things to do with monoidal categories. Nothing to do with the more general structure of the two category. That's something in the fourth lecture to address. Okay. So now I'm going to introduce some more structure that lives naturally on a monoidal category and doesn't live naturally immediately, or does live in some way on the two category perspective. So now we specialise in monoidal categories, we can now add this extra structure. So we say a monoidal category is symmetric when every pair of objects is equipped with a morphism like this, which we draw as these crossed y's, satisfying these equations. If we cross the y's and then cross them again, that gives the identity. And if I've got any two morphisms here, f and g, followed by crossing, that's the same as doing the crossing first, and the g and the f. So the idea is that these y's have their own identity, and the boxes can flow over the crossing and exchange positions. So that's a very natural sort of practice. Coherence property must also be satisfied, which should be very evident if we were doing this all in the pasting diagram approach. There are equations that have to be satisfied using these symmetry morphisms and the associator maps alpha. But once again, in the graphical calculus, these are trivialized. algebraic structures here. I talked at the beginning about sets, those are zero-dimensional things, the monoids are one-dimensional, two-dimensional. There's a general notion of n category. N category is n-dimensional subsets. Now, all of these things we're talking about fit into a big, beautiful picture. So it turns out that just as a monoidal category has a slick definition, it's a two-category with one object. So a symmetric monoidal has a slick definition as a four-category with one object, one morphism, one two-morphism. But we won't worry about those sort of things here. My personal belief is that while we know very well what these low-numbered categorical structures have to do with science, with computing, or as we're discovering, as we're investigating in these lecture courses of the Bob and I are giving, so in the future we will discover what these high-numbered category structures have to do with computer science and with quantum theory and so on. That's for another school anyway, maybe another century. Who knows. Now, in monoidal categories, we can define privileged morphisms called states and effects. So state is a morphism with nothing coming in. Effect is a morphism with nothing coming out. We do all of these things. By the way, I haven't really explicitly said it. We have a temporal interpretation of all of these diagrams. This is if time is flowing from bottom to top. It's common Bobston as well. These are very important interpretations. The state describes preparation of the system. So initially we have nothing, then this thing phi happens, and then we have a system. Okay. There could have been other ways, phi prime, phi double prime, in which we could have prepared these systems. These are the different states that the system have. Now an effect, which is dual in this geometrical sense, right, because the picture is just the upside down picture, describes a post-selection of a system. So what does this mean? This is something that does come up a lot in physics and science. It's surprising perhaps that it has such a primary role to play in this categorical approach. The idea of a post-selection is that you take your system and you grab it and you say, I demand that you are in state psi. Okay. Now in the real world you don't get to just demand whatever you want. You can try, but you don't succeed. So you make this demand and you inspect the system, demand you to be in state psi, it may simply happen that it isn't. In which case the interpretation is that we restart the entire procedure and we try again. And we keep trying until our assertion succeeds. Post-selection succeeds. Now it may be that our post-selection can never succeed. Okay? That we're simply making a demand, perhaps this psi, we can't say much about this here, right, because this psi is just by itself, but maybe this psi is in the context of some much larger complex procedure. Maybe it's the case that this post-selection can never succeed. We're demanding our system to be in a state which it can never be in, given the history of what's gone before. In that case, what will happen is sort of answered in different ways by the different mathematical realizations of this structure, that is, by the different actual interesting monoidal categories that we're working in. Typically what happens is that the whole system just vanishes. The whole state vanishes. You just get zero. You get null. You get halt. You get, I don't know, you get error. You get, but a little light goes off inside your machine that says, I've broken that. So a state is an insistence that in the future, the system, in the state, an effect or post-selection is the insistence that in the past, the system was in this state. So they're dual notions. Actually, these post-selections are beginning to have much more, play a very important role in foundations of physics. In quantum gravity, some people have written papers describing how these post-selections can explain the sort of paradoxical phenomena involved with black hole evaporation. So there's a general idea of time-symmetric quantum mechanics. A strange phenomenon of ordinary quantum mechanics, which has confused a lot of people, famously written about it by Roger Penrose and so on, is that it seems we have very good control over the initial time boundary of our system. That is, we can set up our quantum system in any state that we like initially. But then after everything runs, it seems we have no control over it at the end. We've just got to do a measurement and get what we get. Why is it we have control over put in, but not control over what we put out. Well, that's just how physics works, that's just how universe works, you could say. A notation like this restores some symmetry. It's just a notation, but it does change the emphasis and it does give you some symmetry. And if you set things up so that you can, you imagine that you can impose past states just as easily as you can impose these future states, and you develop that, that's something that's called time symmetric quantum mechanics. It's been used by Okay, so here's an example of a sort of more general picture. Okay, this is no particular importance, this particular example of that. The idea is, goal of categorical quantum mechanics is to represent really interesting processes like quantum teleportation, which was represented before, using states, using effects, and using more general processes. And not only to look at them and say, isn't that pretty, but prove things about them, prove that they're correct, prove that they do something interesting, based on the categorical properties which we perhaps define in the first place.
Jamie,
Yeah.
can I go back to the previous one? So these pictures you're describing in a monoidal category, is that
Yes.
right? And your whole approach is to basically generalize from monoidal to the two categories where you have more regions than just this.
Well, so the focus of this lecture course, at least initially, will just be on the monoidal categories, and I introduced everything via two categories just for a bit of fun, really, because you can. And it's not really more complicated. But in the last lecture, I will show how two categories can be used in a natural way to describe some. The extra structure of the two categories can really be useful in letting you describe quantum computational processes. But for the main chunk of these lectures, we're just working with monoidal categories, not with two categories. So, so far no examples, right? What if no monoidal categories existed, right? This could be the case, right? It's just a contradictory set of axioms, perhaps they don't be no good. So, of course, many of them exist, and this is our motivation. The monoidal category F hill is defined as follows. There's objects, finite dimensional Hilbert spaces, morphisms bound with linear maps, composition of linear maps in the ordinary sense, identity morphisms and identity linear maps. Okay. So these are ordinary sort of structures that, say, if you take a standard course in quantum information or quantum mechanics you would learn about, you wouldn't think of organising them as the objects morphisms on a category, of course, but they fit there very naturally. Tensor product operation, which is our horizontal composition that allows us to put these next to each other. For a monoidal category, we typically call it a tensor product. It's just the ordinary tensor product of Hilbert spaces. The unit object is the one-dimensional Hilbert space. We have to define these associators and these left unitors and these right unitors. Okay. So this is common to how a lot of monoidal category theory works. Most of the time, because of the power of the graphical calculus, you can forget about your associators and unitors and coherence and so on. But you have to check in the beginning that it all works. You've got to check that associators exist, you've got to check their inversion, you've got to check they satisfy coherence equations. Otherwise, the graphical calculus, which doesn't even depict any of this structure, that is, it assumes it's all there and is working as it should, would be no good. So you can't completely forget about this stuff. So, as a little aside, sometimes people say, well, it turns out that somehow because of the way the graphical calculus works so nicely, every monoidal category is equivalent, in a strong sense, to a different monoidal category, in which all these things are completely trivial. Actually, they're just identity morphisms. Strict. And so, some people say, well, this is great, it means that you've no longer got to worry about monoidal categories. You only need to use strict monoidal categories, it says that's true. And then we could just stop here. We needn't have given this structure. Trouble is that, in fact, not in this case F hill, but in general, what happens is that makes the associators unitors a lot simpler, but it can make the whole rest of this category a lot more complicated. Turns out that if you go from a monoidal category to an equivalent strict monoidal category, you can enormously mess up the definitions of your objects and the morphisms and your tensor product. So all that will do in many cases is shift the complexity from the existence of these associators and their coherence properties to the new, more complex definitions of objects and morphisms and their classes. Actually, for the case of FA, that doesn't happen. There is an equivalent knowledge category, F hill, which is strict, where in fact everything gets a lot. So in general, that's not the case. And the general case is important to us in quantum mechanics, and we seek to be more general than just working with spaces. Okay, so what are these associators? Well, they're totally straightforward things. Excuse me, these little circles should be tensor product symbols. If we have an element of H tensor J tensor K, we're going to send that to a canonical element of H tensor J tensor K, just in this way, right? If we've got state phi tensor psi tensor psi, we're going to send that to the state phi tensor psi tensor psi. Right? So I'm defining this associated linear map on the separable states of the Hilbert space, but because it's linear, that in fact defines it on the whole tensor product. Similarly for these left and right units. So all of the structure of finite dimensional Hilbert spaces, in fact, arbitrary dimensional Hilbert spaces, fits very naturally into the structure of the monoidal category. So I've got a few minutes left. This is something I've got a few seconds left. Okay, why don't you say that? Oops, I said that. That's great. So the last important thing to cover is the notion of adjoints. So each linear map of finite dimensional Hilbert spaces has an adjoint. So the notion of reduction of adjoint linear map is standard in functional analysis. You learn the first course of Hilbert spaces. The idea is that the adjoint linear map goes in the other direction. F goes from H to J, F dagger goes from J to H. And you can check that it has these properties. The adjoint of G composed with F is the adjoint of F composed with the adjoint of G. The adjoint of an identity is the identity. If you take the adjoint twice, you get back to where you start. Now, if you think about what that means, it's just saying you have a contravariant functor on your category. Assuming you know what a contravariant functor is, you can Google it. Now, why is this so great? Because we can use it to recover the inner product on the elements of our Hilbert spaces, H and J. How do we do this? Well, suppose we've got some element phi and some element psi. These are elements of the Hilbert space H. So we can think of them as linear maps from the complex numbers into the Hilbert space H that take the number 1 into that chosen element. It's a canonical isomorphism between elements of the Hilbert space H and morphisms from C to H. And what we can do is we can form this composite phi followed by psi dagger. Of course, we're using this contravariant functor dagger to turn psi into psi dagger. By the definition of the adjoint of the linear map, that's the same as phi dagger acting on phi acting on 1. Sorry, that's just immediately what this is saying. And that's again immediately what this is saying. And then the definition of an adjoint is that you can take things across the inner product and replace psi dagger with psi. So this composite just equals the inner product of these elements, phi with psi. And that's great, because the inner products of elements of Hilbert spaces give you the transition amplitudes for any experiment that you perform. If you prepare your system in state phi, you measure it in state psi, the probability for that measurement to be successful will be the square of the norm of these complex numbers. It's extremely important that we can compute these complex numbers. And this contravariant functor gives us a structure to do that. That's a very important point. Okay, that's there.